Hey, hello there. So today I'm talking about question 684, redundant connection, and it's a follow-up of question 685, redundant connection 2. So the only difference between these two questions is that the first question is a undirected graph. The second question is the directed graph. So that direction in the graph is causing the problem to be a bit more difficult. So let's look at the easier one first. So in this problem, a tree is a undirected graph and it's connected and it has no cycle. So if we think about trees, we have tree nodes and they are connected. If we distinguish the direction, we got the parent to child direction. We also have the child to parent direction. So let's think about it a little bit more semantically. It will be the parent of and child of direction. But in the undirected graph, we don't distinguish this directions. All we have is the edge that's connecting two nodes, a parent and a child. Which one is parent, which one is child? We don't know. The graph is connected so that we don't have isolated nodes and we don't have multiple separated disjoint connected component. All we have is a single connected component, that's the tree, because every node has to either have a parent or have a child, have some child. So that's why it's a single connected component. That's a connected graph. There is no cycle because every node is not gonna connecting to some kind of a remote ancestor, and it's not going to have any kind of cousin connections inside the graph, inside the tree. So on the same level, there is no horizontal connection, and there is no node that's connecting to some ancestor that's not its immediate parent. There is no such thing. So we have a graph that's converted from a valid tree with n nodes valued from 1 to n with one additional edge. So, and that edge is not being introduced with an extra node, it's only connecting to existing node here. So you just think we have a valid tree and we draw one extra link to connect to existing node inside the tree. That edge is going to cause a cycle. So the tree is no longer a tree anymore. Here is talking about the input format for the graph. It's the edge list. So we got a list of edges, and the edge is a tuple of two nodes that's been connected. And we got this relationship that u is less than v, which is totally useless in this problem. We want to find a edge if removed, and the resulting graph will again become a valid tree. So it's definitely going to be one of the edge inside the cycle. So there could be potentially multiple edge we can remove to make the graph become a valid tree again. So if there are multiple answers, we should return the answer that occurs the last inside this edge list. So since that we are looking at the last one, we can process this edge list from the left to the right, and the one that's causing trouble is going to be the one that we want to return. We will see this in the example very soon. So just going to copy some example and starting to actually doing this tree building process, looking at the edges, and see when we're actually going to see this cycle, and is that edge introducing the cycle the one that we should return. Just gonna verify this kind of very this intuition, not really intuition, the guess, just going to be verifying that with the example we have. So we have a node that's value 1 is connecting with a node with value 2. We don't have edges, or we don't have directions, the edge is just undirected. We have another node with value 3 that's connected with 1. That's if we try to sort of reconstruct the tree based on the edge we have. So far so good. 1 could be the root, has 2 child, or 2 can be the root. It has child with 1, and the 3 is the child of 1. So either way, we don't know which one is the root. Then we try to introduce this extra edge that's connecting 2 and 3. This edge is indeed going to cause a cycle. If we don't know the order, just imagine that we don't have the order. Remove either one of the edge here can have the tree, the graph to be a valid tree again. but since that 2, 3 is the last one, that's the one we should remove. So you can see based on this example, if we indeed try to reconstruct the tree using the orders from the edge list, the first edge, the edge that's gonna introducing the cycle is the one we should remove and we should return. So that's just based on the first example. Let's talk about another example. So we have node 1 connecting to node 2. Node 2 is connecting with node 3. So far so good. Node 3 is connecting to node 4. We are following this edge list order to reconstruct the tree from the graph. And then we have node 4 trying to connect with node 1. This is the first edge that's introducing the cycle, and it's indeed the one we should remove. So if we remove this, it will become a valid tree again. Sorry. So there's one more node. Oh, sorry. Oh, no. Let's move this down. Yeah, so if we remove the edge between 1 and 4, it will become a valid tree. So that's pretty much the intuition we get from these two examples. So how are we gonna do this? You can see that if we try to form the links, we basically union these two nodes together, and to detect a cycle. It's basically saying that we union node 1 and 2, it's forming a component, it's forming a tree, and 2 and 3, so 1, 2, 3, they all belong to the same component, they all belong to the same tree. We're adding 4, 1, 2, 3, 4, they all are in the same connected component, so they are connected somehow using some intermediate nodes. Then we try to connect 1 and 4. Before we do the actual connection, we just do a really quick test. Are these two nodes already belong to the same tree? If it's belong to the tree, then connecting them, we're going to be causing the cycle. So this is the edge that's going to causing the cycle. So with the union find, all we need to do is in the union code do a really quick test to check whether the two nodes belong to the same connected component. If that's the case, we just gonna that's gonna be indicative of the problem causing edge. So yeah, so just gonna grab the union find code here, templates, and notice that in the union part, what do we do if we do the union by size? That's what happens after this. But before we actually do the union, what we do is to grab the two root nodes, root, the connected component representative, that's telling us whether these two things are in the same connected component. If they are the same, if we actually do one more union to connect them, you're gonna cause the cycle. So here we're just gonna return a boolean instead of the regular union find that's just return nothing. It's void function. But here we actually want to modify this function to be a union, to be a boolean, return a boolean type. If we indeed did the union, we return true, so we can actually connect these two nodes. Otherwise, we return false. This false is telling us this edge is the problem-causing edge. So with this, we should just pretty much follow the tree building process using the order from the edge list. Whenever the first case when we find we got a false from the union operation, that's the edge we should return. So all there left is to determine how many number of nodes we have in this graph. So every edge is connecting two nodes. So for that reason, if it's a, we got, let's say we got n different edges, we're gonna have n plus 1 nodes. Yeah, and indeed we have one extra, so the number of edges are actually going to be the same as the number of nodes. We have 1, 2, 3, 4 different edges, and right, 1, 2, 3, 4, 5. We have five edges, and we got 5 nodes. So yeah, so that's going to be the variable, the amount we need to initialize this union find data structure. So n is going to be the length of these edges, and we're actually going to increase this by 1 because the nodes here are indexed, has values from 1, it's not from 0, so we basically waste one of the slots. The 0 slot here is going to be useless, but it makes the code a lot nicer. So initializing this union find data structure, and for all the edges inside this edge list, we're processing them in the sequential order. If we can do a actual union, we want to continue to process the next edge. Otherwise, it will be the problem-causing edge. So, yeah, so that's it. That's the code for this question 684. If we're using union find, we only did a little bit the modification, convert this union from the usual void to a Boolean type function. That's telling us these two nodes are already in the same tree. They are connected in some way already. If you add one more link to connect them directly, that's going to cause a cycle. So that's the edge we want to return. Looks like a runtime problem. What's the problem? Invalid syntax. Okay, so not very fast, but anyway, the runtime for this is just processing the edges one at a time towards the end. How many edges we have, how much the runtime is, and the space, it's how many nodes we have, how many space we use. So it's linear with respect to the number of nodes, linear with respect to the number of edges. So that's the time and space complexity. So let's look at the follow-up question 685, redundant connection 2. Now the graph is a directed graph. So the direction is telling us the UV, where U is the parent of child V. So when we look at the edge list here, the first node, the first element inside this edge is going to be the parent to the second one. So looking at the graph, the problem will actually have edges now, have arrows now. So 1, 2, 1, 3, and 2, 3. So that it's no longer a cycle, but rather two parents trying to claim the same node as the child. So just gonna try to read if there are other things here. So we have a rooted tree. There is exactly one node for which all other nodes are descendants of this node. That's a definition of a root node. Plus every node has to have exactly one parent, except for the root node which has no parent. So looking at this example, that's exactly the problem happening here. Node 3, if we're connecting to 2, 3, that node 3 will have two parents, so that's going to be causing problems. Since that the 2, 3 is introduced later than this other two, we can remove 2, 3. So here we can no longer remove 1, 1, 2 to make this thing a valid graph. We are making choice between 1, 3 and 2, 3. thinks the 2, 3 is introduced later, that's the one we should remove. So how we can do this very quickly without really doing any kind of union find? Notice that every node will actually just have one in-degree. It's going to have one parent, one parent. So the in-degree is 1, but this particular one here has 2 in-degree. And whatever that edge is causing the second in-degree is the edge we need to remove. So if all we're dealing with inside this directed version of the problem is 2 nodes that's claiming the same child as same node as the child, all we need to do is to find the node with the second in-degree and find the edge that's causing that second in-degree. That's the edge we should remove. So working with in-degree counter, that's what we can solve this. Looking at the second example here, we just put the arrows back to the graph. 1 to 2, 2 to 3. Oh, sorry. Three to 4, and 4 to 1. So in this and 1 to 5. So in this problem, in this example, the problem is not 2 nodes trying to claim the same node as child, but the good old cycle. So the original union find can catch this cycle thing. If we have the order of the union to make sure that when we actually call the root, it's indeed the root of the tree. So we should pay attention to the union operation to make sure that if we do the union, the parent is actually going to be the parent. But if we can make sure that the good old union find solution for the first question should be able to catch this cycle and should be able to tell us this 4-1 is the problem. But notice that we have 2 type of problem: the 2 node trying to claim the same node as child, and this good old cycle. What if they're gonna happen at the same time? Because we already see that we can deal with this with the in-degree catching, and this we can deal with that with the good old cycle detection. If there's no chance this 2 gonna happen at the same time, we can just handle this one first. If there are no node with in-degree 2, that's just going to be the cycle. We can just use union find. So in the worst case, it's going to be 2 paths to solve this problem. The complication comes in when we actually try to combine these 2 problems together. Oh, sorry. So let's say that we have a node 1 and it has a node 4 as a child, and now we have 2 nodes that are trying to claim this node 1 as the child. I'll just move that up. Yeah, just like this. So this will be the first case. Two nodes trying to claim the same node as child. There is no cycle yet, so we can add a cycle by maybe connecting 4 with 3. So this will also introduce a cycle. Notice that in the case when we have it's not connected. In the case that we have both the cycle problem and the 2 parent problem, we want to remove the parent-child claiming violation edge that's inside the cycle. We don't want to remove this 2-1 link. We want to remove this 3-1 link. So that's if we did this in degree checking, we are pretty sure that's going to be we can identify this 2 edge, but which one is in the cycle. Yeah, so we can do separately. One thing we can do is to to try to find these two links, and also try to find the cycle. If they both exist, we're just gonna find which one of this edge is inside the cycle. So that's a potential way to solve this. It's perfectly fine. We do the two parent child edge finding in the first pass. In the second pass, we detect a cycle. If only one of those exists, we can easily return the edge we want to return. If they both exist, we want to explore the cycle and find which of those two edges is the one that's inside the cycle and return that one. That would do. The other way of doing it is just notice that inside this graph, if we remove this two parent to the same child claiming edge, it's a valid graph, so we can process this with no problem. There's not going to be any cycle. Note that indeed in this very combination case, the cycle, if the cycle, the problematic one is the combination. It's the two parent edge. Also, that one is gonna be inside the cycle. So if we remove this two edge, don't consider this two edge in and just process the edges as usual to construct this graph. There's not gonna be any cycle. Then we can find is whatever that the parent to child claiming edge that's going to happen first inside this original edge list, that's the one that's going to cause the problem. So that's the one that's going to be in the cycle. So otherwise we would just remove the latter one. So the another more code elegant way of solving this is still do this, the two parent to same child edge, identifying that, and just move those two edge in their original order to the back of the edge list, and resume this, start over the tree building process. And if the first edge, among these two parent edge, edge is gonna happening, if that's gonna causing a cycle, that's the one we return. If that's not causing any problem, let's say it's 2-1, then we definitely would want to remove the latter one. So it's a little bit confusing, but I guess when you see the code, it will become very clear. So we're just gonna copy the first solution over here. There's nothing we need to change for the union find. The body would remain largely the same, because in a special case, in the second case, it's reduced back to the cycle finding. So the additional thing is to calculating this in degree and identify the conflicting child claiming edge. So what we do is to parents, that's going to be, we're calculating the in degrees. So that's the in degrees, and then excluding those two edges, the tree is gonna be okay. So we're just gonna postpone the decision making, dealing with them. We're gonna reorder this edge list. So that's going to be two parts. The first part is going to be the n-1, potentially n-1 edge that don't contain this the edge that's claiming the same node as child. And just concatenating the two child claiming conflicting edge toward the end. So this code is not super efficient, but it's simple and it's readable. We're gonna put the regular OK edge first, and just concatenating those you know, the two edge that's claiming the same node as the child. So that's why this int degree is 2 towards the end. And then we're just gonna do the usual cycle detection. If there is indeed an edge that's causing the cycle, that's the one we return. And otherwise, we just return the latter one that's causing the child claiming problem. So which is going to be whichever the edge is in the end. So yeah, so indeed, if all we have is the two edge claiming the same node as the child, we're not going to be able to find any cycle. But in the end, we just return the latter one, because the question asks us to return the last problem-causing node. If there is a cycle, we can. If there is only a cycle, this will work. If we have both, we're gonna find the first one that's causing the cycle. So we're gonna find the first among those two parent, two parent problem nodes. Yeah, it's working. Not very fast, but I guess this part is not very efficient. But at least the code is very readable and pretty much the same as the prior question. So yeah, so that's these two questions.